So if you plot the time response for underdamped second order system, for systems like this, where this is the envelope of the system, this is for first graph. If you are having this graph, then your poles are shifting from this to this. So if you are looking, the complex conjugate pole pair is at point 1, then you will get a graph like this. If it is at point 2, then you will get a graph like this. And if it is at point 3, then you will get a graph like this. The oscillations keep on increasing, right? Now, if your pole pair is shifting in this direction, in the real axis direction, then the graph is moving like this. If it is at position 1, then the graph is this. If it is on the farther from j omega axis, then the graph shifts from 1 to 2. Similarly, if your pole pair is moving in this direction, then the graph is shifting like this. This again is a very useful diagram you can draw in your note. So let us do one numerical problem in which the transfer function is given by this. Gs is 100 upon s square plus 15s plus 100. You have to find TP, OS, and TS. So what you need to do is just substitute the formula. TP is pi upon omega n 1 minus zeta square. OS is this and TS is this. So please try to solve this and find out whether you are getting the same solutions or not. Meanwhile, I'll take your attendance. Attend to your roll call. System response with additional poles. Suppose you are having response of higher order systems, which is the sum of response of first order and second order systems. So if you have a transfer function Cs by Rs like this, B naught Sm B1 Sm minus 1 Bm minus 1 S up to Bm, A naught S square plus A1 Sn minus 1 up to An minus 1 S plus An. So this is the transfer function form. This is the pole zero form. You can convert this transfer function form into this pole zero form and find out the poles and zeros of the system. Now, usually CS is composed of real poles and pairs of complex conjugate poles, so that for a step unit for a step input, it can be expressed like this: A by S plus sigma j varying from 1 to q, Aj upon S plus Pj plus sigma, this is the simple pole, plus sigma bks plus sigma k omega k plus ck omega dk upon s square plus 2 sigma d omega ds plus omega k square. Okay, this is the complex conjugate pole pair part. So if you take the inverse Laplace transform, you get the system CT. This will be CT, not CS. CT becomes equal to A plus summation AJ e to the power minus PJT plus summation BK e to the power minus sigma K omega KT cos omega DT plus summation CK e to the power minus sigma K omega KT sin omega D KT. So formula describing percentage overshoot, settling time, and peak time were derived only for a system with two complex poles and no zeros. In other words, if a system has more than two poles and has zeros, we cannot use this formula to calculate the performance specifications that we derived. However, under certain conditions, a system with more than two poles or zeros can be approximated as a second order system that has just two complex dominant poles. Once we justify this approximation, the formula for percentage overshoot, settling time, and peak time can be applied to higher order systems also. All right. So system response with additional poles. Suppose we are having a system has two complex poles at minus sigma. First of all, you write down this formula because this is again important. If you have this, then only you can proceed forward. Conditions for approximating a three-pole system as a two-pole system. How do we do that? Suppose that a system has two poles, complex poles at minus zeta omega n plus minus j omega n under root 1 minus zeta square, and a real pole at minus alpha r. Thus, a step response can be a by s plus this plus this. If you solve this, take the inverse Laplace transform, you get this expression. Okay. Now, three cases of alpha r are to be studied. Case number one, when alpha r is not much greater than zeta omega n, the real pose transient response will not decay to insignificance at the peak or settling time generated by the second order pair. Thus, the system cannot be approximated by a second order system. Right? Now, case 2, if alpha r is very, very large as compared to zeta omega n, then the pure exponential will die out rapidly. Then the second order underdamped step response in such a way that the parameters such as percentage overshoot, peak overshoot, and settling time will be generated by the second order underdamped step response component. Thus, the system can be approximated by a second order system, right? This can be neglected. Now, case 3 is if alpha r is infinity, then in that case, the system is second order system itself. So a rule of thumb is that the exponential decay corresponding to a real pole is negligible after 5 time constants. This is a simple thumb rule. All right. So I want you to take down the notes. Now let us study the system response with additional zero. So this is the system in which we have two complex conjugate pole pair and a additional zero at additional pole at minus alpha r. So this is case 1. So case 1 has this response characteristics. Case 2 is when alpha r2 is very far away from the j omega axis, then the shape of the curve then takes this form. And in case 3, when alpha r is at infinity, then this is the case 3. Okay. So you can note down this. Now, system response with additional poles. What about the magnitude of exponential decay? Can it also be large? That is contribution at the peak time, which is not negligible. So we next see the residual of third pole in a three-pole system with dominant second order pole and no zeros. So if this is the transfer function of the system, then the how actually decrease in magnitude as the third pole is moved farther away from the left half of S plane. Okay. Now let us look up at the step response of a three-pole system. Suppose this is a three-pole system in which we have this. So if you take the partial fraction, then you get this solution. You can find out the value of A, B, C, and D, and then you can get all these values. So please do it yourself. I am giving you time. If you take C as approaching to infinity, that is non-dominant pole approaches infinity, then A becomes equal to 1, B becomes equal to minus 1, and C becomes equal to minus A, and D equal to 0. So thus the residues of the non-dominant pole and its response becomes 0 as the non-dominant pole approaches infinity. Okay, the designer can also choose to forego extensive residual analysis, since all system designs should be simulated to determine final acceptance. In this case, we use the 5 times thumb rule as a necessary but not sufficient condition to increase the confidence in the second order approximation during design, but then simulate the complete design. All right, now let us take another numerical problem. Find out the step response of each of the transfer functions shown below. So I am giving you this as an exercise. All right, I'm uploading this on the Google Classroom. All right. And submit that also today. Please upload the solution today itself. All right, now the class is over.
कि ये स्टेप रिस्पॉन्स निकालना है तो आर एस अपन सी एस अपन आर एस लिखेंगे, फिर इनवर्स लैपलास
यस
निकालना है।
करेंगे। इनवर्स लैपलास निकालना है बस।
ओके मैम, आर एस वन बाई एस
वन
पिछले
बाई
वाले।
एस। हाँ, स्टेप रेस्पॉन्स का मतलब यही होता है, आर एस वन बाई एस लेना है। ठीक है।
ठीक है।
ओके।